Analyzing the movement of galaxies or atoms begins with the same foundation, an object moving along a single straight path. This car on a straight road represents the most basic form of movement we can measure. To track that movement, we first establish a fixed reference point, known as the origin. This point, O, serves as the zero mark for every measurement that follows. When an object's position changes relative to that origin over time, like an athlete running to the 100-meter mark, it is in motion. If its position remains constant at O, the object is at rest. If the athlete runs 100 meters out and then runs back to the 40-meter mark, we have two different values. The distance is the total path covered, 160 meters. But the displacement is only 40 meters because it only measures the net change from the starting point. Displacement depends on the direction of travel, not just the ground covered. This makes the plus and minus signs on our number line essential for describing where an object actually ends up. These two ways of measuring position lead to two ways of measuring rate. Dividing the total distance by time gives us average speed, while dividing displacement by time gives us average velocity. When velocity changes over time, we measure acceleration. For a car speeding up from 0 to 20 meters per second in 4 seconds, acceleration describes how much that velocity increases every second. We calculate this by taking the change in velocity, final velocity minus initial velocity, and dividing it by the time interval. This relationship can be rearranged to isolate the final velocity. By multiplying the acceleration by time and adding the initial velocity, we can determine how fast an object will be moving at any given second. This resulting equation allows us to predict an object's future velocity, provided the rate of acceleration remains constant throughout the motion. Consider a ball thrown straight up that falls through the hoop and returns to the player's hand. If the ball reaches a height of 40 centimeters before falling back, what is the total distance and displacement? The ball traveled 40 centimeters up and 40 centimeters down, covering a total distance of 80 centimeters. But because it returned to the exact height where it started, the net change in position, the displacement, is 0. This result shows how distance and displacement can diverge. Even after traveling a significant path, if the final position matches the initial position, the displacement is mathematically 0. To solve more complex problems involving constant acceleration, we use a specific set of equations that relate displacement, velocity, and time. These equations rely on 5 variables: S for displacement, T for time, U and V for initial and final velocity, and A for acceleration. Memorizing formulas is just the first step. Mastery requires identifying which variables are provided in a problem and which must be calculated. Take a problem where a train starts from rest and accelerates uniformly to 20 meters per second in 10 seconds. To find the distance traveled, we need to extract the data hidden in the text. We begin by listing our 5 variables as a checklist. This organizes the information and reveals exactly what we are missing. From rest tells us the initial velocity, u, is 0. To 20 meters per second gives us a final velocity, v, of 20. And the 10 seconds provides our time, t. We are solving for distance, or s. Since we don't have acceleration, we can't solve for distance in one step. We first use the velocity equation to find the acceleration, and then use that value in our displacement formula to find the total distance. To summarize, distance tracks the path, displacement tracks the net change, and these 3 equations connect them to velocity and acceleration. Always account for direction by assigning positive or negative values to your variables. By identifying your known variables and selecting the equation that connects them, the motion of any object moving in a straight line becomes predictable and mathematically clear. Calculations in physics aren't always found in a simple list of variables. Often, the most important data is hidden in plain sight within the lines of a graph. Take this top-down view of a red car moving along a straight highway. As the car travels, we can plot its exact position on a vertical axis against the passing time on the horizontal axis. If the car maintains a steady speed, the data points form a straight diagonal line. But if the car accelerates, that line bends upward, showing that the car is covering more ground with every passing second. Measuring the steepness of that diagonal line, its slope, gives us the exact velocity of the car at any given moment. On this velocity time graph, a vehicle goes from initial velocity u to final velocity v over time t. The slope, vertical rise, v minus u, divided by horizontal run, t, represents acceleration. Rearranging this formula gives our first kinematic equation, v equals u plus at. This equation is the direct mathematical translation of the slope we see on the velocity time graph. Beyond the slope, there is another physical value stored in the geometry of this graph. The total area between the sloped line and the time axis represents the displacement of the object. We calculate this area by splitting it into a rectangle and a right triangle. The rectangle's area is u times t. The triangle's area is 1/2 base times height, or 1/2 at squared. Adding them gives the second kinematic equation for displacement, s. Every meter the car covers on the road is accounted for in this shaded geometric area. Physics problems often ask for a final velocity while withholding the time interval. Without a horizontal axis value, we need a way to link velocity to distance directly. We solve this by eliminating the time variable. We take our definition of acceleration, rearrange it so t equals v minus u divided by a, and substitute that into our displacement equation. When we expand that substitution, the time variables cancel out across the equation. This links the initial speed and distance traveled directly to the final velocity, resulting in the third equation, v squared equals u squared plus 2as. The third equation is the necessary tool for calculating motion when the duration of the trip is unknown. This graph shows a vehicle reaching 20 meters per second in 6 seconds. Slope is rise 20 over run 6, yielding acceleration of 3.33 meters per second squared. Displacement is the triangle's area, 1/2 times base 6 times height 20, totaling 60 meters. Applying these two visual calculations, slope and area, provides the solution to the majority of linear motion scenarios. Using these equations in the real world, such as maintaining a safe distance behind the truck in this image, requires absolute precision in your calculations. These kinematic equations are only valid if the object is moving with a constant acceleration. If the acceleration changes, the straight lines on our graphs would bend, and the formulas would no longer apply. Because velocity, acceleration, and displacement are vectors, the positive and negative signs in your math tell the story of the object's direction. This summary links the visuals to the algebra. Position time slopes represent velocity, velocity time slopes represent acceleration, and the area under the velocity line represents displacement. Connecting the geometry of the graph to the logic of the equation ensures the motion of the car and the numbers on the page remain perfectly in sync. Imagine you're driving down a highway, and the truck in front of you suddenly hits the brakes. To avoid a collision, you have to know exactly how far your car will travel before coming to a complete stop. By tracking just a few details about your current motion, we can calculate your exact future position. We do this using 3 specific formulas, known as the kinematic equations. These equations allow us to calculate the missing pieces of any straight-line motion problem on a physics exam. To use them, look at 5 specific variables: displacement, labeled s, time interval, t, initial velocity, u, final velocity, v, and acceleration, a. The strict rule: these equations work only if acceleration remains absolutely steady. If acceleration changes, the tools break. Knowing these 5 variables sets the board. Now we need to see exactly how they link together to calculate the outcome. We begin with the standard definition of average acceleration. It is simply the change in velocity divided by the time it took for that change to happen. If we multiply both sides of the equation by time, t, we isolate the change in velocity on the right side. By moving our initial velocity, u, to the other side, we get final velocity by itself. This gives us our first kinematic equation. Now let's calculate displacement, s. If we multiply a constant velocity by a duration of time, the result is displacement. On a graph, that product is represented by the area of a rectangle. Even when velocity changes, that geometric relationship holds. The total area underneath the graphed line represents the object's displacement. We can calculate this total area easily by splitting it into 2 basic geometric shapes, a rectangle at the bottom and a triangle sitting on top. Add the area of the rectangle and triangle together. We already proved in our first equation that v minus u is equal to at. By swapping out that piece in our area formula, we arrive at the second kinematic equation, linking position and time. These first two equations handle most situations, provided the problem actually gives you the duration of the movement. But what happens when an exam question leaves out the time entirely? We need a way to solve for motion without relying on the t variable. To build an equation without time, we go back to our first formula, rearrange it to solve for t, and plug that result directly into the t slots of our second formula. After expanding the terms and cleaning up the algebra, the formula simplifies into our third kinematic equation, completely free of the time variable. You now have a complete set of tools. When faced with a problem, list the 3 variables you know and the one you're trying to find. Then choose the equation that deliberately ignores the 5th unmentioned variable. Let's test this strategy. A race car starts from rest and accelerates at 4 meters per second squared for 5 seconds. Find the distance covered. Pause the video and give it a try. We start by listing our knowns. Initial velocity is 0, acceleration is 4, time is 5. We need displacement. Final velocity isn't mentioned at all, so we cross it out and use the second equation. Plug in the numbers, and the answer is 50 meters. Solving kinematic problems isn't about guessing formulas. It's a precise process of elimination based on what data is absent. There is one final detail that consistently trips students up: direction. Because we are working on a straight line, we have to designate one direction as positive, making the opposite direction negative. Take a car moving forward. Its velocity is positive. But if the driver hits the brakes, the acceleration is pulling in the opposite direction. You must plug a negative value into your equation for that acceleration. With that rule in mind, get ready to take a screenshot. This next screen is everything you need to solve linear motion problems. Here are your 3 equations, aligned directly with their missing variables. Keep them straight, watch your positive and negative signs, and remember the strict condition: the acceleration must be constant. By identifying these 5 variables and applying the correct equation, you can mathematically predict the exact position and speed of any object moving with constant acceleration. Look at this green marble circling inside a roll of tape. It is moving at a perfectly steady, constant speed. So here is a question that trips up a lot of physics students. Is this marble accelerating? The instinct is to say no. In everyday language, acceleration means speeding up or slowing down. But in physics, even though the marble's speed is locked in, it is absolutely accelerating. To understand why, we need to look at what is called uniform circular motion. This happens whenever an object travels along a circular path at a constant speed. Getting comfortable with this strict difference between how we use the word acceleration in normal conversation and how it functions mathematically is the first step to mastering motion in a plane. Let's break down the rules of velocity. Velocity is a vector quantity. That means it requires 2 distinct pieces of information: a magnitude, which is the speed, and a specific direction. Watch what happens as our object moves from point A to point B, and then to point C. The length of our arrow stays exactly the same because the speed is steady, but the direction of travel is continuously shifting as it rounds the curve. Because that direction is constantly changing, the velocity is changing at every single point along the circle. You cannot have a constant velocity if your path is turning. Now let's look at the standard formula for average acceleration. Acceleration is equal to the change in velocity divided by time. If the velocity is changing, which we just proved it is, you automatically generate a mathematical acceleration value. This is one of the most common traps on a physics exam. An object in uniform circular motion is constantly accelerating precisely because its direction never stops changing. Once we know an object is in uniform circular motion, we can calculate its exact speed by adapting the formulas we use for a straight line. Instead of measuring a straight highway, our total distance is the perimeter of the circle. If you unroll that circle into a straight line, the distance of one full journey is the circumference, which we calculate as 2 pi r. Since average speed is just total distance divided by time, we take our circumference, 2 pi r, and divide it by the time it takes to complete one revolution. That gives us our standard equation for speed in uniform circular motion. Let's test this with a quick active recall scenario. Imagine an athlete running exactly one full lap around a circular track. What is their total displacement? And based on that, what is their average velocity? Exams love to use full lap scenarios to verify that you understand the strict mathematical difference between the total distance traveled and the net displacement. Displacement is the straight line shortcut from your starting position to your final position. Because the runner crosses the exact same starting line where they began, their net displacement is mathematically zero. Average velocity is calculated using displacement, not distance. So if the displacement is zero, the average velocity for that full lap is also zero, even though they were running at a high average speed the entire time. If the forces keeping an object in that circular path suddenly disappear, the object will not keep curving. It will fly off in a straight line. This is called tangential velocity, because the instantaneous velocity always points directly along the tangent of the circle. Let's put all the pieces together into a quick mental cheat sheet. Uniform circular motion means traveling a circle at a constant speed, calculated as 2 pi r over t. But remember the chain reaction. A constant speed plus a continuously changing direction equals a changing velocity, and a changing velocity guarantees acceleration. Keep that unbroken link in mind, and you will be able to solve any circular motion problem they throw at you.